Okay, I'm gonna get started today on Unit 14. Um, this is kind of I think, one of the culminations to complexity theory and just computational theory in general is this idea. We're going to talk about P versus NP and what are called NP complete problems this week. We're also, it's going to lead us, we're going to need to talk a little bit about space complexity and what that is for things. And a lot of computational theory is tied into these ideas, P versus NP and NP complete, and what that means. And so we will, for the learning activity this week, we'll have you prove or walk through some proofs of showing how one NP problem can be reduced to another NP problem, but basically showing that a problem is NP complete there. But to get there, we've got to kind of understand what NP is versus P, and that's what we're going to start with today. So I'm going to go to the readings and the videos. I'm going to rely on a number of videos today because this is like the P versus NP lecture is like the classic lecture in computational theory, in a lot of, in computing a lot here. So there's a lot of examples of people giving this lecture out there. And some of them do a very good job, at least at different parts of it. So I'm going to kind of do a best of and pull certain parts out of some different presentations of this today. We went over this last week somewhat in our readings. Chapter 10 in Hopcraft talks about these intractable problems, and that's what when we start talking about NP, that's what we're really talking about is these hard problems here. And again, Zipser just talks about time complexity and builds into this there. And both of them get into this NP versus P stuff relatively quickly. One of the things we're going to want to do is show that problems are equivalent to each other, algorithms are equivalent to each other. I really like this explanation. This is the short introduction to P versus NP, which is okay, but I really like when they talk about these equivalent games here. So I'm going to play the 31st half a minute is just introducing the problem, and then she talks about these equivalent games. And again, it's kind of fun to watch because that's what we're going to be showing is like, how do we show two things are equivalent or reduce one to the other for this? So let's watch this first one here. Okay, let me get this so I can.
About a problem set, often involves the biggest unsolved problem in computer science, P versus NP. There's currently a $1 million prize waiting for the person who solves it. It can roughly be translated to, if the problem is easy to test a solution to, is it also easy to find a solution to? This question sounds crazy, like how could this possibly be? So in this video, we're going to see what all the hype is about, why it's even interested in the first place, and a whole lot more about the nature of computer science. We're going to start in a somewhat unexpected place by playing a game. This game is called Numbers Scrabble, and it's you versus me. First, I'll pick one of these numbers, 1 to 9. Then you pick a number. The aim of the game is to pick 3 numbers that add up to 15. Whoever does this first wins. If all numbers are picked and no player has exactly 15, the game is a draw. Now, how would you go about winning this game?
So again, this is classic game where you have the numbers 1 to 9, and again, you want to get the first one to 15. You want to pick a number, but you also don't want your opponent to get to 15 here. So you're picking numbers and trying to get up to 15 and trying to keep your opponent from getting 15. Again, each number can only be used once. So once it's picked, it's done. So
You can do the trial and error, spend time trying to automate or getting the good name. What would be right now if you'd like to think about it for real? Let me know what you come up with in the comments below. But what can we do right in the game? Instead of lining up the numbers in a line, let's arrange them in squares. Numbers are arranged in a very specific order. Every triplet adds to the state. 2 plus 7 plus 6 is 15. 6 plus 5 plus 4 is 15. 6 plus 1 plus 8 is 15. This is called a magic square, where every triplet has 16 numbers. Try to bring the addition of the triplet, and what we are coming through doing the same thing. Or when we arrange number travel in a magic square, we see really the same way. So a lot of things can be reduced to the exact same way, and a lot of problems in mathematics science can be reduced to the exact same problem. It's just
So yeah, that's what we're going to be kind of looking at is this idea is that if when you first look at a problem, you think, well, I don't know anything like it, but if you kind of rearrange it and do some changing, you can make it into another game. So they're able to, convert this game into basically tic-tac-toe idea. And so that's what we're going to be looking at a lot. Once we get one NP complete problem, well, anytime we have a problem, we're going to try to show that we can take another NP complete problem and reduce it to the problem we have in some way. So this is going to be important for that. The rest of this video is okay and walks you through, what NP completeness is and stuff like that. But I don't think I really like that example. So we're going to start there. I'm then going to go to MIT for an actual introduction to this complexity theory. So this isn't their first one. They've been talking a little bit about P and NP, but they provide a good introduction to this. And this is a long video. We're going to watch quite a bit of it here and there.
The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare.
One thing nice about complexity theory and this sort of stuff is this video is 10 years old and it's still not really that out of date. I think you still have played Mario Brothers. The main question in my mind is, have you played Mario Brothers? And so that would be helpful this video here. So
Continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
Today, this entire field in one lecture. Should be fun. I actually taught an entire class about this topic last semester, but now we're going to do it in 80 minutes. And we're going to look at lots of different problems, from Super Mario Brothers to jigsaw puzzles, and show that they're incomplete. This is a fun area. As Trini mentioned last class, it's all about reduction. It's all about converting one problem into another, which is a fun kind of puzzle in itself. It's an algorithmic challenge, and we're going to do it a lot. But first, I'm going to remind you of some of the things you learned from 006 and tell you what we need to do in order to prove all of these relations, what exactly we need to show for each of those arrows, why it's interesting. So this is generally around the P versus NP problem. So remember, P is all the problems we know how to solve in polynomial time. Well, not just the ones we know how to solve, but all the ones that can be solved. It's pretty much topic of 6006 and 6046 up till now, but for now, in the next few lectures, we'll be talking about problems that are probably not polynomially solvable and what to do about them. Polynomial, you know, is like n to the constant, polynomial good, exponential bad. What is n? I guess n is the size of the problem. Okay, which we'll have to be a little bit careful about today. And then
So again, they're just looking at any problem that can be solved in like polynomials, n squared, n cubed, n to the 12th power, sort of idea. So anything like that, anything that's not exponential or factorial sort of idea. And again, n is the size of the number. So again, sorting is a good example of a polynomial, or is a problem that we can solve in NP, so it's less than this sort of stuff. And again, it goes up depending on the size of n. So
NP is not problem solvable not in polynomial time, but it's problem solvable in non-deterministic polynomial time. So, and in this case, we need to focus on a particular type of problem, which is decision problems. Decision just means that the answer is either yes or no, so single bit answer. See why we need to restrict to that kind of problem in a moment. And probably be solved in polynomial time, same notion of polynomials, same notion of n, but in a totally unrealistic model of computation, which is a non-deterministic model. In a non-deterministic model, what you can do is say, instead of computing something from something you know, you can make a guess. So you can guess one really many options. With complete constant time operation in regular models, like you add two numbers, or you do an if, that sort of thing. Here we can make a guess. I give the computer polynomially many options I'm interested in. The computer's going to give me one of them. It's going to give me a good guess. Guess is guaranteed to be good. And good means here that I want to get to a yes answer if I can. So the formal statement is if any guess would lead to a yes answer, then the yes. The metric is biased towards yes, and this is why we can only think about decision problems, yes or no. You can bias towards no, you get something else called co-NP, but we'll focus here just on NP. So the idea is, I'd really like to find a guess that leads to a yes answer, and the machine magically gives me one. If there is one, which means if I end up saying no, that means there was absolutely no path that would lead to a yes. So
a lot of times when people talk about n versus NP, you kind of think, oh, polynomial time and non-polynomial time, but the NP is not the opposite. They're not like two disjoint sets here, right? So P is polynomial time, NP is these non-deterministic polynomial time. So like magic computer sort of stuff. It reminds me of quantum computing and the idea that quantum computer could try out all, with superposition, all possible combinations and find the right combination. So if there is a solution, it can it can give you an example of that right solution, and then you just have to check if it's right or not. So it'll give you the best solution it can, basically. That's what he was trying to say with this idea. If there's a yes solution, and so again, we're looking at only decision problems that are answered yes or no, but a lot of problems we can rephrase as decision problems here.
When you get a no, you get a lot of information. When you get a yes, you get some information. But hey, you were lucky. Hard to complain. So this in 006, I often call this the lucky model of computation. That's the informal version, but non-determinism is what's really going on here. So maybe it's useful to think to get an example. So here's a problem this is the sort of granddaddy of all NP complete problems. We'll get to completeness in a moment. 3-sat.
Okay, before we get to the 3-sat, I'll just we do have some prompts this week for you to go through. Okay. And so again, we're talking about P versus NP and P completeness, and then we're going to go through some problems. And the first one is this 3-sat problem, and it's a simplified version of the SAT problem. And so this one will have three groupings of three here for this. So just, you might want to do this prompt here and read about that as we're, when we're looking at this. And we'll jump back to that prompt after we kind of walk through this video here.
Like this, like example. Your representation. This is an and. These are ors. Using this for negation. So, in other words, I'm given a formula which is an and of ors, and each or clause only has three things in it. These things are called literals. Variable x of I, or it's the negation of a variable, not x of I. Okay, so this is a typical example. You could have no negations. You could here have one negation, two negations, any number of negations or clause. These groups of three, these four are three things, three literals are called clauses. And they're all ended together. And my goal is this should be a decision question. So I have a yes or no question. And that question is, can you set the variables? I get to choose a true or a false designation, such that the formula comes out true. CNF for true or false. So I want to set these variables such that every clause comes out true because they're added together. So I can satisfy this clause in one of three ways. Maybe I satisfy it in all three ways, doesn't matter. As long as at least one of these should be true, and at least one of these should be true, and at least one of each clause should be true. Okay, so that's.
So again, that's this 3-sat problem. Again, we group these three statements, true false statements together with ors, and then we and those groups together there. I think like he was explaining, so a clause here is true if any of the three things are true, and then we have to make sure, and then all the clauses have to be true because we have this and, they're all ended together here. So if we look at the prompt, let's go here. So I'm trying the new O4 Mini, which is this new ChatGPT model that's out here that does some thinking and stuff. So I asked it about fed it this prompt here. Again, it's a special case of the Boolean satisfaction problem, SAT. So three-sided is that stuff. It's a conjunctive normal form where each clause contains at most three literals here, and the literal is either X or not X. Again, at MIT, they're drawing a line above X to make it negative. Here, they're using this little, I don't know what this symbol is. I call it the not symbol here. In computing, I'm used to doing exclamation point before it to say not. But so whatever notation you want for it. And again, because three-sided restricts each clause to three literals, it remains one of the canonical NP complete problems here. Just so you know, we usually write it with three, but you can actually say at most three because you can reuse a symbol. So if you want to say X1 or X1 or X1, you could do it that basically just one symbol, or you can repeat these symbols there. So it's easy to write this since you can reuse these symbols in the triplet to convert it to a one or a two here. So here's their concrete example: A or B or C, and not A or B or not C, and not A or not B or C here. So here's our different clauses. And again, we're given that A is false, B is true, and C is true here. So the first clause, A is false. We need one of them has to be true. B is true. So as soon as we see B is true, then the whole clause is true. So then it's true here. Clause 2 is not A. A was false, not A is true, so that's true. So that means this whole clause is true because again, or this or that is one. If one of them is true, it's all true, so that's true. And the last clause is again not A. As soon as we see not A, we know since A was false, this is true, so this is true. So all three of these clauses are true, 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 and then F is satisfiable because it ended together, they are all true here. That makes sense? There's three logical. Okay, so now we're gonna prove that NP is
the three-step problem. This is a hard problem. We don't know polynomial time algorithm. There probably isn't one, but there is a polynomial time non-deterministic algorithm. So this problem is in NP because it's kind of designed to solve this kind of problem. What I'm going to do is guess whether X1 is true or false. I have two choices, and I'm going to ask my machine to make the right choice, whether it should be true or false. Then I'll guess X2. Each of these guess operations takes constant time. Do it for every variable. And then I'm going to check whether I happen to satisfy the formula. If it comes out true, then I'll return yes. And if it comes out false, I'll return because NP is biased towards yes answer, it always finds the yes answer if you can. If there's some way to satisfy the formula, then I will get it. If there's some way to make the formula come out true, then this algorithm will return yes. If there's no way to satisfy it, then this non-deterministic algorithm will return no. That's just the definition of how non-deterministic machines work. A little weird. But you can see from this prototype of a non-deterministic algorithm, you can actually always arrange for your guessing to be at the beginning. And then you do some regular polynomial time checking without deterministic checking. So when you rewrite your algorithm like this, with guesses up front and then checking, you can also think of it as a verification algorithm. So you can say, you know, your friends.
So he's going to end in these verification algorithms, and this is what, when we actually normally talk about NP completeness and this sort of stuff, we kind of skip over the non-deterministic idea and just phrase it. So we're gonna rephrase what this means as a verification algorithm, and that is what we're gonna generally use.
Claims that this preset formula is satisfiable, meaning there's a way to set the variable so that it comes out true. This is called a satisfying assignment. Satisfying must be make true. I don't believe you. Your friend says, no, really, it's true. And here's how I can prove it. You said X1 to false, you said X2 to true, you said X3. Basically, they give you the guesses. And then you don't have to be convinced that those are the right guesses. You can check that it's the right guess. You can compute this formula in linear time, see what the outcome is. If someone tells you what the xi's are, you can very quickly see whether that was a satisfying assignment. So you could call this a solution, and then there's a polynomial time verification algorithm that checks that solution's valid. But you can only do that for yes answers. Your friend says, no, this is not satisfiable. They have no way of proving it to you, right? I mean, other than checking all the assignments separately, which would take exponential time, there's no easy way to confirm that the answer to the problem is no. But there is an easy way to check the answer is yes, and then give you the satisfying assignment. Okay, so this definition of NP is what I'll stick to. Is the sort of, I like guessing because it's like dynamic programming. With dynamic programming, we also guess. And guessing actually originally comes from this world, non-determinism. In dynamic programming, we don't allow this kind of model, and so we have to check the guesses separately. And so we spend a lot of time. Here, magically, you always get the right guess in only constant time. But it's a much more powerful model. Of course, there's no computers that work like this, sadly. Or I guess more interestingly. So this is more about confirming that your problem is not totally impossible. At least you can check the answers in polynomial time. So that's. You can take a non-deterministic algorithm and put the guessing up top. You can call the results of those guesses a certificate that the answer is yes. And then you have a polynomial, a regular old deterministic polynomial time algorithm that, given that certificate, will verify that it actually proves that the answer is yes. Yeah, it's just that the certificate has to be polynomial size. You can't guess something of exponential size. You can only guess something of polynomial size. Okay, so.
And again, this is what we'll be using a lot, is these decision problems. And the main thing comes down to, if you're given a solution, can you verify that that solution is correct in polynomial time there? And so a lot of these problems like this one, it seems like obvious, but there are problems where you're given a solution and it's not that easy to verify that it's a correct solution. For example, in chess, if you have a chessboard laid out where pieces are, in a certain spot, and the question is, what is the next best move? And or what move will lead to a winning game for you? And you say, oh, and you're given a solution. This is the move. It's very hard to prove that move will result in a winning game. That you have to try out all the possible combinations and see that one of the paths does lead to a winning game there. So I mean, there are problems where where we can't find a polynomial time verifier, but in a lot of our examples, we'll be able, I mean, like this one here, where we're just given this question here like this, given uh, a three-stat problem equation here and the assignments, it is relatively easy, certainly polynomial time, to be able to plug those in and determine if that's true or not. So there are a lot of problems, well, a number of problems, and that's where we'll be focusing on, where we can do this in polynomial time, determine if we're given a solution that it is correct. Verify, that's what he's talking about.
Seems a little weird, but we'll see why this is useful in a little bit. So let me go to completeness. So that's the problem is. Please. If X is in NP and X is NP hard, it's maybe you remember what was says that. Yeah. I need to define reduce. I can do that as well. Talk about all these.
So what he's getting at is that we're going to be showing that a problem is NP complete. We've got one of the things is it has to be an NP, so that you basically we want to show that given a solution we can show that solution is correct in polynomial time. So that's the first step. And then if it's NP hard, basically means that is there another problem in NP complete that reduces to it there. I think he should have wrote, he said if X is NP hard, if every problem Y element of NP complete reduces to X there. And that's what he's going to show here. Miss writing on chalk. I grew up teaching all on chalkboards. Oh, it just makes me feel, I just feel the chalk and the writing. Oh, it used to be so nice. I miss, I miss this sort of lecture. So I used to study this way. One of the funniest things is, and you see these sliding boards. I had a big physics lecture room. And so before exams, like the final exam, I would go in and I'd like to study in the exact seat I was going to take the lecture in or be in the same room. So one day, and so to review, I'd often write all the problems and solutions out on the board. So I wrote all the problems that I thought were going to be on the exam on the boards there, and then just kind of quickly erased it, not very well. And it filled up this whole room like this. And then usually at night, people come in and clean the board. But I was studying so late for the exam, I studied after the cleaners came by. So the next day at 10 o'clock in the morning, when I sat down at my exam, my notes were still on the entire on all the board. They were erased. I had erased them, but I could still, I mean, it's like this, you can still make them out a lot. So.
Okay, a lot of definitions. But the idea of NP hardness is very simple. If the problem X is NP hard, it means that it's at least as hard as, it's a lie. It's at least as hard as all problems in NP. And I want, intuitively, X means it's at least as hard as everything in NP. Whereas being in NP is a positive statement. It says it's not too hard. At least there's a polynomial time verification algorithm. So being in NP is good news. It says you're no harder than NP. NP hard says you're at least as hard as everything in NP. And so NP complete is a nice answer because it says you are exactly as hard as everything in NP. No harder, no easier. If you draw in the same sense computational difficulty, one axis, which is not really accurate, but I like to do it anyway. And you have P is all of these easy problems down here, and NP is some larger set like this. NP hard is from here over. And this point right here is NP complete.
We're going to return to this at the end of the video with another video with kind of that or other diagrams here. And so this is just a linear one, but basically showing that P is polynomial time. NP includes P because it's any problem that can be done where we can show the solution. If we're given a solution, we can show that it works in polynomial time. And certainly if you can solve the problem in polynomial time, you can do it. You can do a solution in that amount of time there. Now, NP hard is more difficult problems, but they overlap. And he has it as one point, and I actually think of it more as a region. I would have preferred him to draw this as a region rather than one point. So there's a region with a bunch of problems in it where these problems are both NP hard and NP here for this stuff. And they call it NP hard, but I actually would call it hard. There are a bunch of hard problems, and some of those are NP hard, meaning that they are NP. So there are hard problems that aren't in NP there. And again, what is a hard? Generally, we kind of classify anything as hard as anything that is can't be solved in non-polynomial, or is the whole non-polynomial. So any factorial complexity problem or anything like that. So much of will be proving this, all these problems that are NP complete, that are in this little overlapping region there.
Okay, being an NP means you're left of this line or on the line. And being NP hard means you're right at this line or on the line. NP complete means you're right there. So it's a very definitive sense of hardness. Now, there is this slight catch, which is we don't know whether P will NP, so maybe this is the same as this, but probably not, unless you believe in luck, basically, unless you imagine that a computer could engineer luck and always guess the right things without spending a lot of time, then P does not equal NP. And in that world, what we get is that if you have an NP complete problem, or actually any NP hard problem, you know it cannot be in P. Okay, so if you have the X is NP hard, then you know that X is not in P unless all of NP is in P, unless P equals NP. And most reasonable people do not believe this, and so instead they have to believe this, that your problem is not polynomially solvable. So why is this true? Because if your problem is NP hard, it's at least as hard as every problem in NP. And if you believe that there's some problem in NP, we don't necessarily know which one, but if there's any problem out there in NP that is not in P, then X has to be at least as hard as it, so it also requires non-polynomial time, something larger than polynomial time. Okay, what does at least as hard mean, though? We're going to define it in terms of reductions. Reduction from one problem to another is just polynomial time algorithm, regular deterministic polynomial time, that converts an input to the problem A into an equivalent input to problem B. Equivalent means that it has the same yes or no answer. We're thinking about decision problems today. what it tells me is that if I know how to solve problem B, then I also know how to solve problem A. Right? If I have a, say, a polynomial time algorithm for solving B, and I want one for A, I just take my A input, I convert it into the equivalent B input, then I run my algorithm for B, and then it gives me the answer to the A problem because the answers are the same. Okay, so if you have a reduction like this, and if, say, B has a polynomial time algorithm, then so does A. Because you can just convert A into B and then solve B. Also, it works for statistic algorithms. So what this tells us is that in a certain sense, it's right. Was it saying if I can solve B, then I can solve A? So this is saying that B is at least as hard as A. I got that right? A little tricky. So if we want,
It's this whole thing. One thing you'll see is counterintuitive is when we come up with a new problem, let's say Sudoku, and we want to show that Sudoku is NP complete there. We don't show that we can reduce Sudoku to a problem in NP complete. There, we do it the other way around. So if we want to show that Sudoku is NP complete, we find an NP complete problem and show how it can be reduced to Sudoku. So we can so that if we find a solution to any of the NP problems, then we can find a solution Sudoku. It's kind of a fine point, but again, it's you see this made a number of places throughout there that we show the reduction in only one direction. Here.
For the problem is NP hard, what we do is show that every problem in NP can be reduced with problem X. So now we can go back and say, well, if we believe that there's some problem Y that is in NP minus P, there's something out here that is not in P, then we can take that problem Y, and by this definition, we can reduce it to X, because everything in NP reduces to X. And so then I can solve my problem Y, which is in NP minus P, by converting it to X and solving X. So that means X better not have a polynomial time algorithm, because if it did, Y would also have a polynomial time algorithm. And then in general, P would equal NP, because every problem in NP can be converted to X. So if X has a polynomial time algorithm, then every problem Y does. Question? Yes, but the reverse question, if A is an NP, then we conclude that B is an NP, and the answer is no. Because this reduction only lets us convert from A to B. It doesn't let us do anything for converting from B to A. So if we know how to solve A, and we also know how to convert A into B, it doesn't tell us anything. It could be B is a much harder problem than A in that situation. That's, I think, as good as I can do that. Other questions? It is really tricky to get these directions right. So let me.
Okay, I'm going to well, I want to do the Super Mario Brothers because I think this is a great example of this analogy. So I'm going to jump, I think ahead here a little bit. Well, here we better walk through this proof stuff because we'll be doing this stuff.
So that's good to know because then we can just give up searching for all of the time algorithm. All the problems we've seen so far have all of time algorithms, except a couple in your problem sets, which were actually NP-complete. And the best you could have done was exponential, unless you were NP. So here's how we can prove this kind of lower bound and say, look, I don't need to look for algorithms anymore because my problem is just too hard. It's hard as everything in NP. So this is just a summary of those definitions. The first thing you do is prove that X is NP in NP. The second thing you do is prove that X is NP hard. And to do that, you reduce from some known incomplete problem. I guess NP hard, but what is it complete? And then P, you do something like what we did over here, which is to give a non-deterministic algorithm, or you could think of it as defining what the certificate is and then giving a polynomial kind of verification algorithm. So do that two problems. Give a non-deterministic polynomial kind of algorithm, or you give certificate and a verifier. Sometimes wrong certificate. I mean, the certificate you can define however you want, as long as the verifier can actually check it, and when it says yes, then the answer to the problem is yes. So it's really the same thing. Just want to say there's some certificate that a verifier could actually check. Okay, so that's proving that your problem is an NP. It's sort of an algorithmic thing. The second part is all about reduction. Now, the definition says that I could reduce every problem in NP to my problem X. That's tedious because there are a lot of problems in the world. So I don't want to do it for every problem in NP. I'd like to just do it for one. Now, if I reduce sorting my problem, it's not very interesting. It says my problem is at least as hard as sorting. Okay. But I already know how to solve sorting. But if I start from an NP complete problem, then I know by the definition that every problem in NP can be reduced to that problem. And if I show how to reduce the NP complete problem to me, then I know that I'm NP complete too. Because if I have any problem Z in NP, by the definition of NP complete of Y, I can reduce that to Y. And then if I can build a reduction from Y to X, then I get this reduction. And so that means I can convert any problem in NP to my problem X, which means X is NP hard. That's the definition. So all this is to say, the first time you prove a problem is NP complete in the world, this happened in the 70s, by Cook. Basically, he proved the tree sat is NP complete. That was annoying because he had to start from any problem in NP and he had to show that you could reduce any problem in NP to tree set. But now that that hard work is done, our life is much easier. And in this class, all you need to think about is picking your favorite NP complete problem. Tree set is a good choice for almost anything, but we'll see a bunch of other problems today from here, and then reduce from that known problem to your problem that you're trying to prove is NP hard. You can do that, you know your problem is NP. Okay, so we only need one reduction for each hardness result, which is nice. And this picture is a collection of reductions. We're going to start from 3 sat. I'm not going to prove it as NP complete, so I'll give you a hint why that's true. We're going to reduce it to Mario Brothers. We're going to reduce it to three-dimensional matching.
Okay, and today I'm going to skip over. We're just going to jump to, he's going to talk about 3 sat a little bit more and how you can show that, how there's a long proof that shows how any NP problem that if you can show it is there, we can reduce that any problem to 3 sat. If we know there's a polynomial time certificate and verifier here. And then we can show lots of things. I'm just going to jump to the Super Mario problem next because I want to get to that. Okay.
Which we don't do in this class. So if you're interested in take 6045. So, which is some people are actually in there like this semester. Cool. Let's do some reduction. This is where things get fun. So
we want fun. You were thinking we're having fun.
To the Super Mario Brothers. So I assume how many people have played Super Mario Brothers? If you want, I hope if you haven't played, you've seen it, because we're going to rely very much on Super Mario Brothers physics, which isn't necessarily intuitive, but if you haven't played, you should, obviously. And we're going to reduce 3 sat to Super Mario Brothers. This is a theorem by a bunch of people, one MIT grad student, myself, and a couple other collaborators outside, not at MIT. And of course, this result holds for all versions of Super Mario Brothers so far released, I think. The proofs are a little bit different for each one, especially Mario 2, which is on universe. But I'm going to talk about the original Super Mario Brothers, NES Classic, which I grew up with. So now the real Super Mario Brothers is, you know, a 320 by 240 screen. It's a little bit small. Once you go right, you can't go back left, except in the maze level. Anyway, so I need to generalize a little bit because if you assume that the screen size of Super Mario Brothers is constant, in fact, you can dynamic program your way through and find an optimal solution in polynomial time. So I need to generalize a little bit. My entire in one screen, no scroll. Never mind, this is the side scrolling adventure. And so that's my generalized problem, and I claim this is anti-hard. If I give you a level and I ask you, can you get to the end of this level? That problem is anti-hard. Okay, also no time limit. Although the time limit would be okay, but you have to generalize it instead of 300 seconds or whatever. It has to be an arbitrary value. Okay, so how are we going to do this? We're going to reduce from 3SAT to Super Mario Brothers. So that means I'm given, I don't get to choose, I'm given one of these formulas. And I have to convert it into an equivalent Super Mario Brother instance. So I have to convert it into a level, a hypothetical level of Super Mario Brothers. Given formula, I have to build a level that implements that formula. Okay, so here's what it's going to look like. I'm going to start out somewhere. Here's my drawing of Mario. Or we could play Luigi, doesn't matter. First thing it's going to do is enter a little black box called a variable. Okay, this is supposed to represent, let's call it x1. Okay, and so there's some black box. I'm going to tell you what it is in a moment. And it has two outputs. There's the true output and the false output. The idea is that Mario has to choose whether to set x1 to true or false. Okay, let me show you that gadget. Here's the variable gadget. So Mario could enter from this way or that way. We'll need a couple of hundred in a moment. And then falls down. Once Mario's down here, if you check the jump height, you cannot get back up to here. So it's like a one-way. Once you're down here, you have a choice. Should I fall to the left or fall to the right? If you make this fall large enough.
So have you guys played Mario enough? I mean, does this make sense that you went down, you couldn't jump back up there because of the size? We'll get into big Mario versus little Mario in a little bit too, so you might want to call that. But again, you can eat the only option, and again, notice you can enter it from the left or the right on this.
When you fall, you can't unfall. So once you make a choice whether I leave on the true exit or the false exit, that's a permanent choice. You can't undo it unless you can come back to here. But we'll set up so that never happens. So, I mean, if you're trying to solve a level, you don't know which way to go. You have to guess. And go fall to the left or fall to the right or do something. The existence of a playthrough, this level, is the same as saying your user choice for the x1 variable. Now we have to do this for lots of variables. So there's x2 variable, 3 variable. Each one has a 2 exit. Level will have n instances of this if we have n variables. Now, what do I do once Mario decides that this is a true thing? What I'm going to do is have this is called a gadget, by the way. In general, most NP-hardness proofs use these things called gadgets, which is saying we take various features of the input and we convert them into corresponding features in the output. So here, I'm taking each variable, x1, x2, x3, and so on, and building this little gadget for each of those variables. Now, the other big thing you have in 3SAT are the clauses. We have triples of variables, or their negations, that kind of have to come together and be satisfied. one of them has to be true. So down here, I'm going to have some clause gadgets. Okay, so the idea is that some of the clauses have X1 in them, X1 with the true version of X1, X1 bar. Okay, so for those clauses, I want to connect. I'm going to dip into the clause briefly. So from this wire, I'm going to dip into the clause here. And then I'm going to go to the next clause that has X1. Maybe it's this one, and the next one, and so on. Okay, all the clauses that have X1 in it, I dip into. The other ones I don't. And then once I'm done, I'm going to come back and feed into X2. Okay. Next, I look at this false wire for X1. So all the clauses that have X1 bar in them, I'm going to connect. So I don't know which ones they are. Maybe this one, something. Okay. And then come here. Okay, so the idea is that Mario makes a choice whether X1 is true or false. If X1 is true, it's going to visit, Mario's going to visit all of the clauses that have X1 true in them. And then it's going to go to the X2 choice. Then it's going to choose whether X2 is true or false and repeat. Okay, or X1, or Mario decides X1 should be false. That will satisfy all the clauses that have X1 equal X1 bar in them. And then again, we feed back into X2. So this is why we have two inputs to the X2 gadget. One of them is when the previous variable is true. The other is when the previous variable is false. The choice of X2 doesn't depend on the choice of X1, so they feed into the same thing, and you have to make your choice. Okay, so so far so good. Now the question is what's happening in these clauses? And then there's one other aspect, which is after you've set all of the variables, at the very end, after this last variable x10, at the very end, what we're going to do is come and go through all the clauses. And then this is the flag. This is where you win the level. All right, do it backwards. So the goal is for Mario to start here and get here. In order to do that, you have to be able to traverse through these clauses. So what do the clauses look like? This is a little bit more elaborate. This is a clause gadget. So there are three ways to get into the clause. It's actually upside down relative to that picture, but that's not a problem. So if Mario comes here, then you can hit the question mark from below. And inside this question mark is the invincibility star. The invincibility star will come up here and just bounce around forever. And we check. The star will just stay there for as long as you let it sit. Unfortunately, all of these are solid blocks, so Mario can't actually get up here to get the star. Okay, but as long as Mario can visit this question mark, or this question mark, or this question mark, then there will be at least one star up here. So the idea is that each of these represents one of the literals in the clause. And if we choose, so let's look at this first clause, x1 or x3 or x6 clause. So if we choose x1 to be true, then we'll follow the path and we'll be able to hit the star. Or if we choose x3 to be true, then we'll come in here and hit this star. Okay? Or if we choose x6 to be false, then that path will lead here and we'll be able to hit this question mark and get the star here. So as long as we satisfy the clause, there will be at least one star. It won't help if you have multiple stars. Then the final traversal part, so that was the first clause, and then we're traversing through. Actually, in this picture, it's left to right. Just turn your head. And so now Mario's going to have to traverse this gadget from left to right on this top part. And if Mario comes in here, you can barely jump over that. If there's a star, you can collect the star and then run through all of these flaming bars of death. If there's no star, you can't. You'll die and try to traverse. So in order to be able to traverse all these clauses, they must all be true. And them all being true is the same as their and being true.
I just find this very creative. I see this every once in a while where people take some problem and try to map it into some other weird problem. I often see, like, I don't know if you know like Conway's Life game, but people will create complex solutions on Conway's Life, show that you can do a Turing machine. So I thought this very creative is, I mean, we have these, given some formula where you have these three variables, or together and then added up, and how do you convert that into Mario levels? And this is just a very creative way of converting this into these Mario levels.
This formula has a satisfying assignment. The satisfying assignment would be given to you by the level play. The choices that Mario makes in this gadget will tell you whether X1 and each variable should be true or false. Okay, so to leverage just a little bit more, in general, when you have a reduction like this, to prove that it actually works, you need to check two things. You need to check that if there is a way to satisfy this formula, then there is a way to play this level. And then conversely, you need to show that if there's a way to play this level, then the formula has a satisfying assignment. So for that latter part, in order to check, in order to convert the level play into a satisfying assignment, you just check which way Mario falls in each of the gadgets, left or right. That tells you the variable assignment. And because of the way the clauses work, you'll only be able to finish the level if there was at least one star here. And the stars run out after some time. So you can barely make it through all the flaming bars of death. Then you get to the next clause, you need another star for each one. Conversely, if there is a satisfying assignment, you can actually play through the level. You just make these choices according to what the satisfying assignment is. So either way, it's equivalent. We always get a yes or no answer here whenever we get a corresponding answer or no answer to the preset problem. And you also need to check that this reduction is polynomial size. It generates or it can be computed in polynomial time. So there's an issue, given this thing, you have to lay this out in a grid and draw all these wires. And there's one problem here, which is
I always love these things where you get so close and then there's always just one little thing. So I love this and how they overcome this.
And that's a little awkward because these wires are basically just one tunnel for Mario to walk through. But what does it mean to have a crossing wire? If Mario's coming this way, I don't want him to be able to go up here. He has to go straight. Otherwise, this reduction won't work. So I need what's called a crossover gadget. Everywhere here, I have a crossing. This gadget has to guarantee that I can go through one way or the other way, but there's no leakage from one path to the other path. Actually, if I first traverse through here and then I traverse through here, it's okay if I leak back because once I visit the wire, I'm kind of done. But I can't have leakage if only one of them is traversed. So this is the last gadget. The most complicated of them all. So this took a while. You might imagine. So this is what we call a unidirectional crossover. You can either go from left to right or from bottom to top, but you cannot go from bottom to right or bottom to left or left to bottom, that kind of thing. Okay, so I'm told that Mario's only got to enter from here to here because all of these wires, I can make one-way wires. I only have to think about going in a particular direction. I can have balls to force Mario to only go one way along these wires. And so let me show you the valid traversals. Maybe the simplest one is from here. So let's say Mario comes in here, falls, but can't backtrack, can jump up here. And then if Mario's big, you can break this block. But if he's big, there should be a couple more zigzags here. Let's try to run. You can crash slide through here. But then you'll sort of lose your momentum and you won't be able to go through all these traversals as.
So I don't remember how that goes, but I do remember, yeah, there's when you get mushroom orb, you get big, right? And it's kind of like a bonus. So they start off big in this case.
You can first take the damage, become a small Mario, then you can fit through these wiggly blocks, but you cannot break blocks anymore as a small Mario. So once you've committed to going small, you have to stay small until you get to here, and then you can get there's a mushroom in this block. So you can get big again, and you can break this block again. Okay, but once you're big, you can't backtrack because Big Mario can't fit through these tiny tubes. Pretty clear, right?
Okay, So I'm gonna leave that if you want. So he goes on and talks about a number of other reductions here and stuff. I'm going to skip those for this stuff. So that's this MIT OpenCourseware. I'm going to jump into a specific NP complete problem, and that's a Hamiltonian cycle problem. First, I'm going to jump back here and see how we're doing. We don't have that much time. Okay. Again, I was asking AI, what is P, what is NP here, and why this matters here. And again, like someone mentioned, there's $1 million prize to prove that P equals NP or that P does not equal NP. It's part of the Millennium Prize stuff. And talks about some issues with this, and then talks about NP completeness. And again, this whole idea of verification, and we don't need to discover a solution for NP, we just have to verify it here for that. Okay, and now we're going to look at, so we talked about this 3-SAT problem, and then we're going to talk about converting that convert that into a Hamilton cycle problem. We just saw one converting FSAT to Mario. We're going to now look at this Hamilton cycle problem. So let's look at that example here.
In our last video, we used the reduction of perfect SAT to show that 3-SAT is NP altered. And now that we know 3-SAT is NP complete, we can use the reduction.
So again, he's starting with 3-SAT being NP hard, or, and then.
I want to focus on the Hamiltonian cycle problem. A Hamiltonian cycle in a directed graph is a simple cycle that visits every vertex. Meaning it starts and ends at the same vertex, follows edges in the graph, and along the way visits every other vertex exactly once. And the Hamiltonian cycle problem is, if we are given a directed graph as input, does that graph have a cycle? To prove that a problem is NP complete, we need to show two things. First, that it's in NP. Second, that it's NP altered. To show that it's in NP, we provide a certificate and a verifier. And as is often the case, our certificate for the decision problem can be the sort of thing that would be an answer to the search for the problem. We don't necessarily have an efficient way to find a Hamiltonian cycle, but if we had one, that would be a proof that a particular graph is a guess instance for this problem. So our certificate can be the order in which the cycle visits all of the vertices, and the job of the verifier is just to check that that view is a Hamiltonian cycle graph. So it'll make.
So we're gonna pull some graph theory ones here. I mean, there's a whole math course in graph theory, which is actually a little helpful for this. But again, not required. We're trying to stick to some. So just so you know, in graph theory, we have these nodes or vertices, and we have edges that connect them. And then in a directed graph, the edges have a direction, and we can only move in that direction. So this is in a directed graph. So we have vertices or nodes, and then we have edges that have a direction. We can only go in the direction given here for this. And so every node should have a direction, although you can have a direction going one way and another edge or going the other way also. That is allowed. So
every vertex of the graph exactly once, and for each consecutive pair in the list, which has a very edge between them, meaning they're adjacent around. And that includes that the last element of the list must be adjacent to the first. And if all of those edges exist, then the certificate shows a Hamiltonian cycle graph and proves the graph is a yes. To complete our proof that this problem is in NP, we have to confirm that the certificate has polynomial sign and the verifier runs in polynomial time. But those are both easy because the length of the certificate is the number of vertices in the graph. And the verifier running time is clearly polynomial because it just has to iterate through the list and check that each edge is in fact present in the graph. And finally, we have to prove that a problem is a yes instance if and only if there is some certificate that will make it the right.
So this is a 23-minute video. So I'm going to jump through it a couple places and show, and kind of highlight this sort of stuff. So again, to show something and be complete, we have to show that we can verify a solution in polynomial time. And again, we can do it. If we can create a verify. He just walked through that. Now we're going to map an existing NP complete problem onto this one. So again, we're going to say we're going to take the 3-sat problem here and show that if we're given a specific 3-sat problem, we can create a graph where finding a Hamiltonian cycle to the graph is equivalent to solving this problem for this. So that's what he's going to kind of walk through here.
Sometimes it's easy to put a lot of work into, say, transforming a Hamiltonian.
He talks about making sure you do this in the right direction and showing that we want to start at 3-sat and go to this, not vice versa. At some point, every one of these TAs probably lost points on an assignment because they were told to do it and they did it the wrong way. And so they all are a little sensitive of this sort of stuff. So just so you know, there is a direction to this.
So when you do these conversions, make sure that you are taking instances going to build very particular types of connected graphs that let us encode all of the information about some Bayesian formula. And if there were an efficient way to solve Hamiltonian cycles in general, then it would also have to handle the weird graphs that encode 3-sat problems, which would mean it would give us an efficient way to solve 3-sat problems, which would mean that P equals N. And since we don't think that P equals N, once we figure out how to do this coding, we'll conclude that we probably don't have a polynomial algorithm for solving N. The way we're going to construct this graph is we'll start with 2 vertices for each variable that appears in the formula. And between those 2 variables, we're going to have paths going in both directions. And we want to set it up so that traveling along the path that goes from the S vertex to the not S vertex corresponds to setting S to true in the formula, whereas going across the path from the not S vertex to the S vertex corresponds to setting S to false in the formula. You'll also have a vertex for each of the clauses in the formula, and we want to set up connections to these clause vertices so that if we're going across in the direction that corresponds to setting a variable to true, you'll be able to pass through the vertices that setting that variable to true would satisfy. But we won't be able to pass through any of the vertices for clauses that would not be satisfied by setting that variable to true. So we'd like to have an edge that if we're going across here in the P equals true direction, we'll be able to visit clause 1 along the way. But we don't want to be able to visit clause 2 if we're going this direction. But if we're going in the P equals false direction, then we do want to be able to visit clause 2 as we go across this row of the graph. And we'll achieve this by breaking these up into a bunch of vertices. Specifically, we'll add 2 vertices for each clause that either the variable or each.
Okay, I'm going to walk through this a little bit. He's going to add these vertices in here. Okay, so basically what he's done is added these nodes in here so that it allows you to go to these closets. So again, from P, you can go here, and then you can go to clause one, and then from clause one, you can go back, and then you can keep going through this and vice versa. Let me slow this down while he explains this again.
Clause one and two, while not two is in four. Each of the rows to allow a Hamiltonian cycle to potentially go across each row in either direction. So we'll add edges from P to Q and also from P to not Q, so that if we end up at P as we go across, we can then go to either end of the Q row and set Q to either true or false. And likewise, we'll add edges from not P to both directions Q, and the same for each of the other rows. And also from the bottom row to the top row to allow us to complete the cycle back to the vertex where we started. So now we've built a graph corresponding to this particular reset problem. And I claim that in general, this procedure for building the graph will give us a graph that has a Hamiltonian cycle if and only if the original preset problem was satisfied. To prove that claim, we need to show that if there's a satisfying assignment in the original formula, that corresponds to some Hamiltonian cycle in this graph, and that if there's a Hamiltonian cycle in this graph, that corresponds to some satisfying assignment. Before we do this example, let's look at this particular example. One way we could satisfy this formula would be to set Q and R to false and S to true. That way, not R makes this one true, not P makes this clause true, not Q makes this clause true, and not P makes this clause true. And
so again, what's kind of important here is that you're given the idea is that you're given a solution, you want to verify it. So you're given an assignment of P, Q, R, and S that are either true or false. And so that means that you're gonna, if it's true, you're gonna, like if P is true, you're gonna start P here and move through over this direction and go to various other things. But it won't be true and false. You're either going to go this direction or this direction, because again, you're given an assignment of this sort of stuff. Same with S, or Q is false. So we're going to start if the Q false and go this way there. So you're given an assignment, and then you're going to have to find your path.
we're talking about cycle, we can start at any vertex, but then we could traverse around the graph and visit every other vertex before we return. Since P is set to false, we'll start our traversal at not P, and we will go across this row in the P equals false direction. And when we get to this vertex, since it has an edge to C4, and then head back to this vertex,
on to now P making this clause evaluated true. When we get to this vertex, we can also pop out to C2 and back along the way, corresponding to making this clause true with P false. But when we get to these vertices, we can't visit C1 without doubling back to a vertex we've already seen. And that's because we set it up so that we could only visit C1 if we were going across in the.
So again, the directions of these lines kind of matter. And again, we want to do a cycle where every node is visited once and only once. And so if he's talking about like here, if we're going across left, right, we can't go here and then come back and then we'll go here again. So then we'd visit this node twice and it's not a Hamiltonian graph here. I just love this diagram. It reminds me a lot of the Mario level also, where again, we're taking some this question and mapping it onto a complex graph of some sort and showing that if we can find these cycles, then we can solve this problem for this. I'm going to skip over again. You can watch the rest of this video where he walks through it, but I just think that's a nice graphical illustration of that sort of stuff. Okay. I'm going to just give our last video is just a short video. It's talks about again, it's one of these 10-minute overviews of P versus NP, but I like how he talks about different complexity areas here. So I'm just going to jump to that area.
No, okay, because fast protein folding would help us cure cancer.
Okay, wait, where are we at? Oh, we're on normal speed. He's just talking faster.
But the fact that a bunch of smart people have all been unsuccessful coming up with fast programs to solve what turned out to be essentially the same problem looks like a pretty good clue that the fast programs just aren't out there. So why is it so hard to prove P versus NP one way or the other? Well, fun fact, proving things is an NP problem. The P versus NP question itself is one of these problems. So yeah, this might be difficult. Or not. We don't know. As the field of computational.
Now, one thing I'd just like to note is that I have lived through a lot of times where we've had problems that we thought could not be solved quickly, and people have come up with solutions to them. I remember first learning about fast Fourier transforms when you have some time signal and you want to convert it from the time domain to space domain and back and forth. We did not have a fast Fourier transform. We just had Fourier transforms, and they were very slow and hard to do there. And at some point, people came up with fast Fourier transforms where they could do this in polynomial time here. And it's like, wow, all of a sudden we had FFTs. When I took this class, primality of determining if number was prime it was unknown, but it was thought probably to be NP, but no one could prove it. But one of the questions you'll look at is what developments have in my lifetime have happened to the whole primality stuff, and is primality testing in NP or not, or where is it?
Complexity is developing. We've discovered a lot of complexity. The P versus NP question turns out to be just the main attraction in a huge and complicated zoo of complexity. Beyond NP, there are even harder classes of problems like X. The class of problems including figuring out the best move in chess that takes exponential time in non-chess. This whole upper area of problems that are at least as hard as NP complete is called NP hard. There's also co-NP, the class of problems where instead of being easy to check right answers, it's easy to exclude wrong answers, which may or may not be the same as NP. And then there's P-space, the class of problems that can be solved given unlimited time, but using only a polynomial amount of space for memory. There are also problems that can be solved probabilistically in polynomial time. That class is called BPP, and it may or may not actually be the same as P. And then there's a quantum computing analog of BPP called BQ. All over the place in here are complicated little classes that will take a lot of explaining. And actually, some of these turn out to be infinite hierarchies of problems that are slightly more difficult than the ones beneath them. We know there's an exponential hierarchy. There's probably a polynomial type. And up beyond all of this are problems that are just not solvable by any computer in any amount of time or space. To me,
okay, so again, we're not going to deal with all of these things. We're just going to mention a little bit some of these as far as the space ones in just a sec. But Again, we're mainly just focused on the main one, which is P versus NP, and what is in NP complete. So, okay, let's talk about the prompts here a little bit. So I think AI is really quite good. Because again, we watch these videos, they haven't changed in 10 years. A lot of this material hasn't changed much in the last 10 years. And so it's pretty good here, even though there's a lot of logic here, it's pretty well-known logic. And there's lots of examples of how you convert from how you reduce one problem to another problem. And so on Thursday, we'll have you work that. We'll create a list of a bunch of NP complete problems and have you walk through a couple reductions for those here. And so as part of the prompts, like here, the Hamiltonian cycle one was the Hamiltonian cycle problem is our prompt. Why is it NP complete? Provide a clear explanation of how the 3-sat problem can be reduced to the Hamiltonian problem. And that's what we just watched as a video. One of the reasons I'm doing videos is that sometimes I find the videos here a little easier. You have to see what you want here. So here Minnie was giving me 2 different solutions here, walking it through here. So this is a little more mathematical here. So our input is a graph sequence of vertices. Check if what order this time is. Why is Hamiltonian cycle NP hard? Talking about this problem here, and a reduction from 3-sat to Hamiltonian problem. So again, we're given these clauses here where each clause is made up of these values. We're creating these gadgets, a variable gadget and a clause gadget, and we connect it all together here. And again, you can kind of read through that and understand it, but I actually like the video where we see the diagram and we see I just like visualizing graphs a lot better than some of these things can give us. So that's what we'll talk about. So again, we have some problems. One of the famous ones is the travel salesman problem. We'll talk about that on Thursday, but we'll also look at some of these other common problems. One of your prompts is this primality test here, and is testing if a number is prime in P or NP there for this. And then space complexity. We don't get much time to do space complexity here, but again, you can talk about what space complexity is and how space is different. And again, that just like you would think, that's just how much memory it would take for this here. And again, we have polynomial space, P space here. And again, you can ask AI these questions. It should give you a pretty good example. So again, and there's also this logarithmic space and non-deterministic logarithmic space questions here. And then the last prompts is that, like, does this help you write better programs? And how could this help you write better programs here? And again, one of the ideas is that if a problem is if a problem is NP complete, if you can reduce a problem or reduce any problems to the problem you're going to solve, then you should be looking for a fast algorithm. You should be looking at an approximation algorithm. So with these problems, we can't solve them, but we can guess or estimate a solution. So we can't like solve the traveling salesman problem to guarantee that our solution is the shortest graph there, but we can find a very short graph for the traveling salesman problem. We just can't guarantee it is the shortest graph of it if we want to do it quickly. So that sometimes that changes how we frame or what we talk about as a solution to a problem here. Okay, so Thursday we will jump into So I want you to go through by Thursday, go through those prompts, and then I haven't done it yet, but we'll have you then walk through these NP complete problems and work on them. What I think I'll do is I'll create a selection of NP complete problems and let you pick which one you want to show as a solution. And there's a couple that we'll all do. We'll certainly all look at the traveling salesman problem too, or each of you will look at that individually. So. Questions on this? There'll be no assignment this week, and on Thursday we'll talk more about the final project and working on that. So no assignment this week. We'll just do the learning activity so that you can be working on the final paper for that. I should say, I think in one of the assignments, I'm going to ask you to do an outline of your final paper, a little draft. So, but I think that's next week. I'll have to look. But again, any sort of assignment will be related to working on the final paper. All right. Questions? All right, let's wrap this up here.